Good afternoon, students. I hope my slides are visible to you and I'm audible to you. So, I welcome you all to the third tutorial of the course Introductory Organic Chemistry 2, which is conducted by NPTEL, whose course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputre from ISER Pune. I am Deepika, your PMRF teaching assistant, and I'm doing my PhD in chemistry at IIT Bombay. So, previously, we have conducted two tutorials on the course, and today we have the third tutorial where we are going to discuss nucleophilic addition reactions to carbonyl compounds, and we will also introduce the topic of stereochemistry involved in case of nucleophilic additions of carbonyl compounds. Before moving to today's tutorial questions, I would like to show my fellow TA for the course, Anisha's YouTube channel. Actually, one of you asked me about weekly assignments. Since we do not have access to weekly assignments of this year, we can only get the previous year tutorial questions or assignment questions. So, Anisha has solved the previous year assignment questions in a descriptive manner. So if you want the solutions of those previous year questions, you can go through her channel. She has uploaded the videos. So in case you couldn't find her channel, like I asked you to go through her channel in last week. So in case you couldn't find, this is the channel, so you can go through it and you will find the previous year assignment question solutions in her channel. Okay, so with this, we are going to solve a few new questions on the topic on this third tutorial of the course. So let us start. So first question of today's tutorial is, which of the following has the largest equilibrium constant for the formation of a cyanohydrine? You are given four options here and you are being asked which of the substrate given will readily undergo cyanohydrine formation reaction when the reaction conditions are given. Okay, so all these four, we know that cyanohydrine is formed by carbonyl compounds. Okay, so all of these four compounds are either aldehydes and ketone. You just have to look at the reactivity of the carbonyl CO bond present in all these substrates. Let us go one by one. First one is given, which is acetaldehyde, and then in option B you are given a ketone. In option C and D again you are given two aldehydes. When it comes to the reactivity towards nucleophilic addition between aldehyde versus ketone, aldehydes are always more reactive because ketone carbonyl group is attached to two alkyl change or aryl change, which are pushing their electron density towards the carbonyl group. So as compared to aldehyde, ketone carbonyl carbon is a little more electron rich. Okay, so when it comes to reactivity towards nucleophilic addition, aldehydes are more reactive. So directly we will eliminate the option B here. Now we are left with option A, C and D. If we look at option C is carrying one ethyl alkyl chain, which is definitely more electron donating as compared to option A. Okay, so if we have to find out the most reactive, that means the least electron rich carbonyl option C can also be eliminated. Okay, so in case of option D, what happens? If we look at the electron pair conjugation, the phenyl ring electrons are in conjugation with this with this aldehydic functionality. Okay, electron can be easily flowed. If you go through the electron flow, it can be donated here, and this CO electron density will run to oxygen, giving you one O minus. That resonating structure is present in case of this phenyl containing aldehyde. So when the Cn minus will attack during the cyanohydrin formation, that conjugation will be lost. For option D, that electron pair conjugation which is extended towards O minus will be lost when Cn minus will attack at this carbonyl, and you will get here OH and Cn. And this loss of conjugation will unfavor the reaction. Okay, always extended conjugation is in organic molecules are favored. So since cyanohydrin formation is decreasing the electron flow chain, this is why option D will unfavor the cyanohydrin formation. So hence we are left with option A, and option A will be the most reactive towards cyanohydrin formation. Okay, and the product will be what? CH3C. One functionality here will be OH, and another will be the incoming cyanide Cn, and here as it is hydrogen. So you will get the cyanohydrin of this acetaldehyde with the largest equilibrium constant. So this is the explanation of the answer. Like I said, steric congestion near the carbonyl of a ketone or an aldehyde inhibits the formation of cyanohydrin. That is why we first eliminated the ketone. And in case of benzaldehyde, like I said, the extended conjugation will be disturbed by the formation of cyanohydrin. So the option A will be the correct answer. I hope this was clear to you. Okay. Then in the next question, which is normally the main product when a mixture of aldehyde RCHO and an excess of alcohol R-OH is treated with an acid catalyst? So you are basically reacting an aldehyde with an alcohol in presence of acid catalyst. So this is a condition of an well-known reaction which is acetal formation. Okay, when aldehydes are treated with alcohol, we in presence of acid catalyst, you get acetal formation. So you are given here 4 options A, B, C, D. In option A, you get formation of only hemiacetal. Okay, and in option B, you can see that one proton from the hydroxyl group of hemiacetal is being taken, but we do not have any base in the reaction condition. Okay, so you cannot get this oxyanion. So option B you can directly eliminate. If you need this compound, you need base for proton abstraction, right? And in option C, you get acetal formation, and in option D, you get acetal, but one proton is replaced by hydroxyl group. But the reaction conditions are simply the acetal formation reaction condition, so you do not get any replacement of hydrogen by hydroxyl group in the reaction. This is why option D can also be eliminated. Okay, so ultimately you will get the acetal formation in the reaction. Simply when you react an alcohol with a carbonyl compound, aldehyde or ketone, in the first step, in presence of acid, you get hemiacetal, but the reaction doesn't stop at that form. One more equivalent of alcohol will add up, and you will get, since you have acid in the reaction medium, you get first oxonium ion formation in this hydroxyl group, and ultimately you get water as the leaving group. Okay, and if you want to know the mechanism in a simplified manner, you can look at this mechanism. Okay, here is the hemiacetal, and in the subsequent step, in presence of acid, this oxonium is forming. An electron push from this alkoxide will lead to elimination of water molecule, which is a very good leaving group. Okay, and in the subsequent step, the second equivalent of the alcohol comes, attacks at the intermediate, and deprotonation of the intermediate formed will finally lead to the formation of acetal as the product. Okay, and thus this is a mechanism which acetal formation reaction follows in presence of acid catalysis. Thus option C will be the correct answer. Then next we have, which is normally the main product, a mixture of aldehyde RCHO and an excess of alcohol R-OH is treated with a base catalyst. So we have already seen that acetal was being formed in presence of acid catalyst. So now what will happen if acid is not present in the reaction mixture, which led to the formation of acetal? In this case, what will we get? Let us look at the mechanism that this reaction will follow in presence of base catalyst. Okay, so what happens? Hemiacetal will anyway form in presence of base catalyst also. Okay, but then like we saw in this step, the oxonium was forming in presence of acid. This oxonium formation will not happen in this case. Okay, because the protonation of the hydroxyl group is not possible since the reaction medium contains only base. No proton is available. This is why this reaction will stop at this hemiacetal form only. Okay, so acetal cannot further form in presence of base catalyst. Which you
नहीं नहीं अभी नहीं बस 3 days पुस्तक आने को करेंगे मेरा नहीं है बताओ जल्दी कौन सा बताओ ब्लूटूथ कौन है
yes, if do you have any queries? Okay, okay, so always remember, in presence of base catalyst, you will get hemiacetal formation in this reaction between an aldehyde and alcohol. Okay, both these conditions are completely based on the catalyst present in the reaction medium. So let us move to the next question. Which of the following reactions does not give the compound indicated as a main product? So you are given 4 reactions and you are asked which of the reaction is not showing the correct product formed. Okay, so let us move to the reaction conditions given to one by one, and we will see what should be the actual product that should be formed in the reactions. Okay, so let us come to option A. You are given this ketone and we are treating it with hydrazine in presence of acid catalyst. So this is the standard reaction condition for the formation of hydrazone from carbonyl compounds, which follows this kind of mechanism. Okay, hydrazine gets added, undergoes nucleophilic addition to the carbonyl carbon, leading to the formation of this oxyanion. And in the next step, this oxyanion can abstract the proton from this NH positive, which can lead to the formation of directly this compound 4. Okay, and then conjugation of electron pairs from this nitrogen leads to the formation of this oxonium, like we saw, because acid is present in the reaction medium. Okay, acid is present, so in presence of acid you will get the oxonium like we saw in the acetyl formation case, and ultimately you will get this kind of intermediate. Okay, and then you have the counter anion of acid in the reaction medium. Like for example, if we are using acetic acid, you will get acetate in the reaction medium, and this will take up a proton from the positively charged intermediate, leading to the formation of this hydrazone. Okay, this positive charge on the nitrogen will get neutralized to give you this hydrazone. So, when we treat a carbonyl compound with hydrazine in presence of acid catalyst, you get a hydrazone. So, we will definitely eliminate the option A because it is showing the correct product that is forming in the reaction. So, let us move to option B. Here you are being shown that this ketone in presence of hydrazine and in presence of sodium hydroxide base under heating condition is giving you hydrazone. But when we looked at the mechanism of hydrazone formation, in the third last step, you were getting oxonium ion formation by picking up a proton from acid in the medium. So if you do not have acid in the reaction condition, how will you get hydrazone? Isn't it? Actually, in presence of base in this reaction, the reaction follows a completely different mechanism, which is our well-known Wolff-Kishner reduction condition. Okay, so when with hydrazine, you do not add any acid, rather you add base like sodium hydroxide, etc. You get reduction of this carbonyl group, and simply you get this alkane as the final product. Okay, so let us look at the mechanism that this interesting reaction follows. uh, First half of the mechanism will be similar to what we saw in the hydrogen formation. First, the hydrogen will undergo the nucleophilic attack to give you this oxyanion, and then protonation deprotonation will lead to the formation of this kind of intermediate compound. Now you have base in the reaction medium. This base will lead to the elimination of this hydroxyl group as shown here. And in the subsequent steps, in presence of the base, these intermediate hydrazone and diamide compounds will be ultimately converted into this alkane by elimination of water molecule. Okay, so in case of base mediated reaction between a carbonyl compound and hydrazine, the reaction will not stop at the hydrazone step. Okay, it will further convert the product into an alkane, and this reduction is known as Wolff-Kishner reduction, which was developed in 1911. So, thus, option B is not showing the correct product that is being formed in the reaction. We already got that, okay? Then if we move to option C and D, these two options are together showing an Wittig reaction condition, okay? What happens in Wittig reaction? You get phosphorus ylide formation first by the reaction of triphenyl or trialkyl phosphine and alkyl halide, and this phosphorus ylide gets added to the carbonyl compound to give you a four-membered oxaphosphetane intermediate. Okay, by the reaction of phosphorus ylide and carbonyl compound, you get a four-membered highly strained oxaphosphetane intermediate, which leads to the formation of alkenes in the reaction. Okay, and this is a well-known reaction condition for the conversion of carbonyl compounds into alkenes. Okay, so option C and D, this was the option C given. Okay, this reaction was given in the option C, and the second step of the Wittig reaction was given in the option D. So, like in the option, you see this is the phosphorus ylide formed, and this is the alkene that should be formed when this phosphorus ylide reacts with this ketone. So you can say that option C and D are showing the correct products that are being formed in these two steps. So now you already know that option B will be the correct answer, that option B is not showing the correct product forming in the reaction. It should be a reduced product of this ketone. Okay, here you should simply get CH2 and then CH3 by Wolff-Kishner reduction. So I hope this was clear, and let us move to the next question. Which of the following statements is wrong? Hydrolysis of an acetal is catalyzed by acids. Hydrolysis of an acetal is catalyzed by bases. Oximes are stabilized by conjugation between the CN and C double bond and OH groups. Enamines are formed between secondary amines and the carbonyl group of aldehydes and ketones. Okay, so we have already looked at the mechanism of acetal formation. Now this question is talking about the hydrolysis of acetal. That is, they are talking basically about the reverse of acetal formation. We got acetal from carbonyl, and now this reaction, this question is wanting carbonyl compound from acetal by hydrolysis, and they are asking in option A and B. If you look at, they are asking you need acids or base for hydrolysis of acetal. Okay, so to know about this, let us look at the mechanism of hydrolysis of acetal. When you treat acetal with acid, you get oxonium ion formation here, and electron push from this alkoxy oxygen atom will leading to the elimination of this good leaving group. Okay, and then you get this positively charged intermediate. Water in the reaction medium will attack at this carbonyl carbon, leading to the formation of this kind of intermediate product. And ultimately, by hydrolysis of this hemiacetal, you will get the elimination of the alcohol which was incoming during the formation of acetal. Then, after the formation of this intermediate, deprotonation from this oxonium will lead to the formation of the parent aldehyde of the acetal. Okay, so this is the reaction mechanism that hydrolysis of acetal follows. So, like you saw in the reaction medium, you need acid for hydrolysis of acetal. Okay, so that when you were given option A and B, that whether you need acids or bases, you have to choose that hydrolysis of acetal is catalyzed by acids. So option B here is completely wrong. Okay, and if you look at option C and D, I will not much emphasize these two, because these two functionalities you already know that yes, oximes are stabilized by the conjugation between C double bond and OH minus. OH lone pair of electrons can be pushed to CN double bond and you get an extended conjugation in that system. We will come to that kind of example in the subsequent questions of the tutorial. Okay, so option C is correct. Option D as well, as you know, like we see in the hydrogen chemistry, enamines are formed between secondary amines and carbonyl group of aldehydes and ketones. So option D here is also correct. Thus, option B will be the correct answer for this question. This particular statement is wrong here. Okay, hydrolysis of acetal is not catalyzed by bases. Then let us move to the next question. Which aldehyde has the smallest equilibrium constant for the formation of cyanohydrine? So similar kind of question we have already solved in the question 1. So let us now try to look at this particular question where all the 4 options are aromatic aldehydes. Okay. So in option A, the phenyl ring is completely unsubstituted, and in option B, you have a meta methyl substitution. Okay, and in option C, you have a methoxy substituent at the meta position of aldehyde functionality. In option D as well, you have chloro substituent in the meta position of aldehyde. So you must remember, when methoxy and chlorine, these two, when they are present in ortho or para position with respect to carbonyl groups, they act as electron, they act with two effects. Okay, like we talked in our previous tutorial, they show mesomeric and inductive, both these effects. But when they are present only in the meta position, these two, as they have lone pair of electrons, when they are present in the meta position, they will only exhibit minus I effect. Okay, so in the meta position, these two will pull the electron density towards itself from the carbonyl group. So in these two compounds, you will expect more reactivity towards nucleophilic addition for these two carbonyl groups, because in this case these two are more electron deficient, since these two are pulling electrons. But when it comes to methyl, which do not possess any lone pair of electrons, when it is present in the meta position, it will behave as in the similar way that it behaves in ortho and para positions. Okay, so methyl in meta position also behaves as an electron donating group. Thus, by donating its electrons towards the aldehyde, it will make this carbonyl carbon electron rich. So if a nucleophile is coming which is already electron rich and might be having a lone pair of electron or maybe negative charge on it. If that species is coming to attack at this carbon and this is already electron rich, then you will expect electronic repulsion between these two substrates, okay? Between this center and between the incoming nucleophile. You will expect a kind of electron repulsion when you have this B as the substrate. And if we talk about A versus B, in A you do not have any substituent in the phenyl ring, whereas in case of B you have methyl in the phenyl ring, which is acting as electron donating group. So now I hope you can already imagine which of these will be the least reactive towards the towards nucleophilic addition reaction. Definitely the one which is most electron rich. Okay, so in case of this question, out of all these four substrates, option B is the most electron rich carbonyl carbon. So for talking about the smallest equilibrium constant for this particular nucleophilic addition reaction, option B will be the correct answer. Okay, and this is the description for the answer. You may note down, and I hope this answer was clear to you all. So let us move to the next question. Which ketone has the largest equilibrium constant for hydration? So in this question, you are given these four ketones, and out of these four, three are cyclic ketones, and option D is acyclic. Okay, so you need to see which of these substrates will undergo hydration reaction with the most feasibility. Okay, for that you have to look at the strain in these rings present. Okay, let us look at the options one by one. When it comes to option A, you have this four-membered cyclobutanone, and as you may already know, 3 and 4-membered cycles are the most strained cycles of all organic compounds. So whenever you have a situation that you are in a 3-membered or 4-membered cycle in a compound, those compounds will always look for release of the strain present in the ring. Okay, and when we are treating these substrates for hydration, you will get an hydroxyl group here. Okay, you will get one hydrogen and one OH here. So this sp2 carbon atom will change itself into sp3 hybridization. Okay, so when sp2 is changing to sp3, definitely this particular angle will be increased. Okay, and thereby when these three cyclic compounds will undergo hydration, upon changing this carbon to sp2 hybridization into sp3 hybridization, angle strain will be released in the rings. And this is already acyclic, so this substrate is definitely more stable as compared to these three. Okay, so you can directly eliminate this option. It is already stable, so when you carry out hydration, these three will more readily undergo hydration than option D, because hydration is releasing their angle strain of the ring. Okay, ring strain is being relaxed. So when you compare option A, B and C, A will be the most reactive one towards hydration so that it can easily release its ring strain. Okay, so option A will be the correct answer for this question. This is the description for the answer. You may note down this. Like it said, the carbonyl carbon changes from sp2 to sp3 in the conversion of a ketone to its hydrate. So there is a relief of ring strain upon the hydration of cyclobutanol. And 5 and 6 membered rings are more stable than 3 and 4 membered. So option A will be the most readily undergoing substrate. Okay, and thus option A will be the correct answer for this question. Let us move to the next question. Which combination of an aldehyde and an alcohol most readily forms a hemiacetal with base catalysis? So we have already looked at the mechanism of formation of hemiacetal and acetal, and we also looked at the hydrolysis of acetal. Now we have this question: which combination of an aldehyde and an alcohol will undergo formation of hemiacetal most readily when you have base present in the reaction condition? Like we saw, in presence of base, the hemiacetal formation step was the main product obtained, and it did not undergo further reaction to give you acetal. Okay, so reaction condition is as it is, which should be given for hemiacetal. You just have to look at the substrates now. Okay, which of these substrates will be the most reactive? And in case of alcohol, you must see the most sterically favorable alcohol. Okay, when we are seeing hemiacetal formation and the incoming alcohol will attack at the carbonyl carbon, you need a more sterically favored alcohol. Okay, so in case of these four options, if you have, you do not need to look at the electron density. First priority should be the sterically favored alcohol, which will not cause any hindrance at this carbonyl carbon while incoming. Okay, so we will directly choose either this or this. Okay, because these two will be sterically hindered alcohols and they will cause steric hindrance at this electrophilic carbon center. So now you have to choose whether option A or option C will undergo hemiacetal formation most readily. For that, you have to look at the aldehyde, right? Which aldehyde is electron rich and which one is electron poor? The electron poor will undergo most readily, okay, because it needs electron. And since the lone pair is attacking, so the incoming electron will be more readily accepted by that carbonyl which is already electron deficient. So when you compare A versus C, definitely you must know that option C substrate is more electron poor because it is containing chlorine at this carbon center. Okay, so when it comes to methyl and chloromethyl, this chloromethyl is making this carbonyl carbon center more electron deficient because of its electronegativity. Thus, you have known that if, as we have already chosen this alcohol as sterically favored reagent for nucleophilic addition, option C will be the correct answer for this. Okay. So this is the description. If you need, you can note down. And like it says, an electron withdrawing substituent facilitates nucleophilic addition to the carbonyl of an aldehyde. Whereas when it comes to alcohol, bulky groups in an alcohol lead to steric hindrance in its addition to a carbonyl. This is why balance of both these two facts will lead to option C being the correct answer. Okay, I hope this was clear to you. And then let us move to the next question. Which of the following most readily forms a cyclic hemiacetal with acid catalysis? You are given here 4 options, out of which 2 are aldehydes and 2 of these are ketones. Okay. When it comes to cyclic hemiacetal formation, aldehydes are more reactive than ketones. Okay, because it is a nucleophilic addition reaction, and towards nucleophilic addition reaction, like I have already described, aldehydes are far more reactive than ketones. Okay, so either option A will be correct or option C will be correct for this question. Now you have to choose one of these 2 options. Okay, let us look at the ring size that will be formed when these 2 substrates will undergo hemiacetal formation. Okay, so what will happen in the hemiacetal formation reaction? This lone pair on the oxygen atom will attack at this carbonyl carbon, leading to the formation of oxyanion, which will be protonated to give you here hydroxyl group. And now in the product, this O is attached to this carbon atom. Then let us count the number of atoms in the ring. Okay, 1, 2, 3, 4. So if this particular substrate undergoes hemiacetal formation, you will get a 4-membered hemiacetal. And I hope you understood how we got the 4-membered cycle. Okay, this will attack here and you get 1, 2, 3, 4. 4-membered cyclic hemiacetal. Now let us come to option C. When this O in this lone pair containing oxygen will undergo nucleophilic addition to the aldehyde, you will get 1, 2, 3, 4, 5, 6. Okay, in option C, you will get a 6-membered cyclic hemiacetal formation. Thus, you have 4-membered versus 6-membered hemiacetal for option A and C. And we know that 3 and 4-membered cyclic compounds are highly strained and their formation will also not be very feasible. So if you compare option C versus option A versus C, you must choose option C as the correct answer. Okay, when you have formation of cyclic hemiacetal, most favored one will be a formation of 5-membered cycle, which will be followed by 6-membered cycle, and the least favored will be 3 and 4-membered cycles. Always remember. Okay, so here in this particular question, option C will give you the most stable hemiacetal. Okay, option C will be the correct answer. This is the description which says that between aldehydes and ketones, aldehydes will be more reactive, and then it says that 5-membered rings will be most readily formed. And since in the option we do not have 5, rather we have 6-membered ring formation, you must choose that particular option as the correct answer. I hope this is clear to you all. Okay, let us move to the next question. Okay, this is based on this reaction mechanism and arrow pushing. So let us move to it. Which stage of the following reaction scheme for acetal formation does not correctly show the flow of electrons? So you are given a mechanism for acetal formation, okay, where these all electron pairs and then arrow pushing are being shown in each of the steps. So we will go through it one by one and we will identify the step in which the arrow pushing is not being shown correctly. Okay. So arrows are basically what? These are showing flow of electrons, movement of electrons in an intermediate or maybe in a step of reaction mechanism. So in the first step, we can see trapping of proton by this oxygen of the carbonyl. So yes, this has electron pairs and it is taking up a proton leading to the formation of oxonium. So yes, electron movement in is shown correctly here. Okay. Electropositive species is taking electron lone pairs. So this step is correct. Simple. And then you have the step B, where the incoming alcohol is attacking at the carbonyl carbon. Okay, so yes, the lone pair of the oxygen of the alcohol is undergoing nucleophilic addition to this electron deficient carbon, and the arrow pushing will neutralize the positively charged oxonium. Okay, so yes, this step is also correctly shown. Electron flow is being shown from electron rich species to electron deficient species. Okay, step B is also correct. Then as a result of step B, you get the formation of step C via this second oxonium. Okay, first what happens, since this oxygen atom is giving away its electron pairs, this will get a positive charge and this oxygen is being neutralized, so you get here a neutral hydroxyl substituent. So no arrow pushing here, so you don't need to worry about this step, but you ultimately get step C. Okay, so what is happening in step C? Let us look. In step C, this alkoxy oxygen is giving away its lone pair of electrons towards this carbon, and in turn the electron is flowing towards the positively charged oxonium. Again, here also you are seeing electron movement from this electron rich species towards this electron deficient one. Okay. Sorry. So yes, this is also following the rules of arrow pushing, and in the subsequent step this water molecule will get eliminated. Okay, and you arrive at this third oxonium species. So what is happening in step D? Let us see. This is now positively charged and you need electron movement towards this oxygen atom so that this can get neutralized. Okay, so for acetal formation at this step, you need the second molecule of alcohol. So yes, you are being given the second molecule of alcohol, but what is happening here? You need to attack the electron deficient carbon to neutralize this oxonium, and the donation will happen from the electron rich oxygen of the alcohol molecule. But in this mechanism that is being shown in the question, this arrow pushing direction is violating the rules. We are giving away electrons from an highly electropositive species to this highly electron rich oxygen atom, which is possessing lone pairs of electrons. So this is completely violating the rules of arrow pushing, and it is showing incorrect flow of electrons. Okay, so you can definitely choose stage D as the correct answer. Okay, in the correct way, if you want to show, it should happen like this. The way it happened in stage B, na? In option D also, this oxygen atom should have attacked at this carbonyl carbon, leading to the neutralization of this positive charge, and which gave you the product acetal. Okay, so the arrow pushing here is reversed in stage D. This is why you must choose stage D as the correct answer, which is not correctly showing the flow of electrons. Okay, so I hope this movement of electrons in this mechanism was clear to you, how we chose stage D as the correct answer. But then let us move to the next question. Which of A to D is least likely as an intermediate or a product in the following reaction? So in this question they are asking, for this given reaction, which of these four products cannot form at all? Okay, and what is the reaction condition? You are being given acid here. So what happens? Let us go step by step. What will happen when we add this amine to this carbonyl compound? This electron rich nitrogen will undergo nucleophilic addition here. And since you have acid in the medium, you will get neutralization of this O minus as OH, and that will lead to the formation of option A product. Okay, so fine, now you know that option A can be formed, but in general what happens for this reaction? The reaction doesn't stop at this A product stage. Okay, it further reacts with another acid proton. So what happens in that case? This hydroxide gets protonated by taking up a proton from the reaction medium, and that leads to the formation of oxonium here. Okay, one water molecule, positively charged water molecule, will get linked here. Okay, and now you need to eliminate this water. For that, what happens? Electron push comes from this nitrogen atom. Nitrogen lone pair will be pushed here, and this water molecule will get eliminated, and that will be the main product that will be formed in this reaction. Okay, and this is the product that we are talking about. I hope you understood how this product be formed. Protonation of this hydroxide will first happen. An electron push from nitrogen atom will eliminate water molecule, leading to the formation of this Chips base. Okay, Option B is the main product in this reaction. So now you know that if we talk about step-by-step conversion, option A and option B both are forming in the reaction. Okay. So now what happens? Let us come to option C. If option B undergoes rearrangement by considering deprotonation by the counteranion of acid, you can expect the formation of option C. Okay, this is basically a rearranged product of this option B. Okay, just you are getting an endo double bond by this isomerization. Okay, so option C is also possible in this condition. But for this particular reaction, option D cannot be formed. Okay, here is the description for this particular option. You will always get an enamine by the reaction of a ketone and secondary amine, and the second amine molecule will not get added up into the enamine. Okay, so basically option B is the most favored product by, but isomerization of this option B can also give you the product C. And also while moving to the formation of option B, you first get option A as an intermediate product. So if you have to choose the least likely product in this reaction, you have to choose option D. Okay, I hope this is clear to you all. So till now we saw nucleophilic addition reactions of aldehydes and ketones. Now we will talk about the stereochemistry involved in these reactions. Okay, for example, in this first example that we are going to solve, when you are adding a nucleophile at this carbonyl carbon, you have two options. Okay, if you imagine this carbonyl group at the plane of the paper or maybe plane of the screen, you have two faces. One is above the screen and below the screen. Okay, so incoming butyl which will be coming, that incoming butyl can attack at this carbonyl from above the screen or from below the screen, and in turn the hydroxide in the final product which you will get by reaction with proton from water, the hydroxide may lie above the screen or below the screen. Okay, so basically there are some rules which governs the stereochemistry in this nucleophilic addition reactions. Okay, and if you have gone through the video lectures, two video lectures were there by Professor Harinath Chakrapani sir. He has very nicely explained the rules of this stereochemistry involved, what happens when electronegative groups are also present in the alpha position, like in this case what happens there, and he has very nicely explained. You can, if you want to revise, you can go through his lectures, and we will also now step by step solve this question. Okay, and we will figure out which one will be the correct major product, and in the major product this hydroxyl will lie above or below the screen. Okay, so let us try to solve this question now. So what happens, this is the substrate that is given. Okay, and by following the rules of Falkin and model and Seepluk model, First, you have to arrange this carbonyl group and this proton in this manner. Okay. In this linear manner, first we will keep the carbonyl and the aldehydic proton. After arranging it in such a way, if in the substrate if you have an electronegative group at the alpha position of the substrate, like in this case you have electronegative atom here with lone pair of electrons, then you have to arrange it in a perpendicular fashion to the carbonyl group. Okay, I hope you understood. Like in the video he explained about C-plug model, we have arranged the electronegative group perpendicular to the carbonyl. Okay, now accordingly we will arrange the other substituents. That is, you have a proton here which will be below the screen, and you have this propyl group also. Okay, so here accordingly we have placed the proton which will be the on the opposite face of this enemy 2. So like in this way we have arranged it. Okay, so after arranging, now you have to figure out the incoming nucleophile will attack at the carbonyl carbon from which side. See what happens, the incoming nucleophile is electron rich, and this electronegative atom which is possessing lone pair of electrons, it is also electron rich. So to minimize electronic repulsion between its lone pairs and the incoming nucleophile, the nucleophile will always attack at the carbonyl carbon from the side of this smallest group. Okay, so following the angle of Burji-Dunitz parameter, the nucleophile will attack from the side of the smallest group, and thereby these two groups will be tilted to this face. Okay, so this is the attack that is basically taking place, and after the attack happens, and what is the nucleophile here? Butyl, na? From butyl lithium. So this butyl is incoming from this side, and it is shifting this O and CO and CH towards this face. Okay, so this will be the orientation of the product that is being formed. So as you can see, the nucleophile is attacking from this way, and OH and H now will be oriented in this manner. Now to write the product, you have to arrange it in such a way that the uh, longest linear chain will be in this anti-periplanar uh, fashion. Okay, so here butyl and this propyl will be the longest chain, so we have arranged it in such a way that butyl and propyl are in this anti-periplanar fashion. And likewise, see, we have moved this propyl to the place of NME2. So following the angle, you have to move the other substituents in the similar way. Okay, this medium group is coming to NME2's place, and thus NME2 will come to the place of this small group. Okay, and also this hydrogen will now take up the propyl position. So to write the product, you have to arrange it in this way. Thus, in this particular reaction, After arranging the two alkyl chains in this way, we get the OH and NMe2 in opposite phases. Like you see here now, NMe2 and hydroxyl groups are lying in the opposite phases. So this will be the major product formed in this reaction. Okay. So to figure out the stereochemistry of nucleophilic addition, you first have to arrange it in this fashion, which is suggested by Falkin-Ahn model, and then you have to attack at the carbonyl carbon by the nucleophile from the side of smallest group. In this particular question, this anti-product will be the correct option. Okay. So in this first example, we had the electronegative model. Okay, we had an electronegative substituent at the alpha position which contains lone pair of electrons. Now in the next question, we do not have such electronegativity theory. We just need to figure out from which side the incoming nucleophile will get added. Will it get added from the pH side or methyl side? And ultimately, if you talk about the methyl, the hydroxide will be cis or trans. Let us figure out. Okay, in a similar way we will figure out, and you will get one of these two products. So simply first we will arrange this CO group and hydrogen in anti-periplanar fashion like we did in the previous example. Okay, in this way we have first arranged, and after arranging the aldehydic functionality in the back side, we will now arrange the substituents. So while arranging the substituents, the biggest group of these three will lie perpendicular to this carbonyl group. Okay, so that no steric repulsion can occur between them. And in this perpendicular fashion, the steric repulsion will be least between these two. So if pH is arranged in this way, accordingly methyl and hydrogen will lie in this fashion. Okay, you are keeping pH perpendicular, so methyl and hydrogen will lie in this way at an angle of 120 degree. Okay, so these two are the possible orientation. Any one of these two you can follow to get the answer. So now after arranging it, we will attack at this carbonyl carbon from the side of the smallest group. So what is the smallest group here? Of course, this proton. So the incoming nucleophile will attack from this way. Okay, and this newly forming hydroxide and hydrogen will get tilted towards these two directions. Okay, and like we did in the previous question, when you finally arrange the longest chain, which will be methyl and phenyl in an anti-periplanar fashion, you will get this hydroxide and methyl in a anti fashion. In a cis fashion. These two will lie cis to each other in the final product. Okay, you have to just attack at this carbonyl by the incoming nucleophile, which will be methyl here. So methyl will attack from this side, and in the product you have to arrange the incoming methyl and this phenyl in an anti-periplanar fashion, which will lead to the cis stereochemistry of the product. Okay, so this will be the major product that will be formed here. I hope this was clear to you. So with this, we have discussed the questions of tutorial 3, and let us quickly revise what we have discussed today. We started with this cyanohydrin formation reaction, where we dealt with the question you had to figure out which of the following had largest equilibrium constant, and for that we figured out the substrate which will be containing the most electron poor carbonyl carbon. Okay, and here we saw that option A was the correct answer, because in all other three the reaction was either unfavored or the carbonyl carbon was very electron rich. And in the next question, we saw what happened when aldehyde was treated with alcohol in presence of acid catalyst. We also talked about the mechanism of acetal formation, and we saw that you need acid catalyst particularly to get an efficient acetal formation. So we saw that option C, acetal, was the correct answer for this reaction condition. So in the next question, we saw what is the main product when aldehyde and alcohol is now being treated in presence of base catalyst. Okay, and we saw in presence of base, we do not get acetal, we only get the first half mechanism for the acetal formation, that is, you get only hemiacetal formation in presence of base. And then in the next question, we saw that out of all these